Hello everybody, and thank you for being here. I would like to inform all of you that the seminar will be recorded. And okay, now we can start. Today with us we have Lorenzo. He's a PhD student here in SISSA, and he is working in collaboration with the data science group. And today he will present a work about Gaussian models, a mathematical framework for the analysis of real data structures. So please, Lorenzo.
Thanks for the introduction. So yes, I will present the work that I'm doing with Professor Sebastian Gold. The idea is to go beyond Gaussian models, and we want study some models that are better to understand the real data structures and develop a mathematical framework to understand them. So the idea, like the problem that we study, is the one of hypothesis testing. So we have two distributions of data. One is pure noise, the other is noise, but there is some signal inside. So we can see in this distribution that there is a direction that is preferred over the other, and then there is also noise, making it hard to find it. And so we get some data extracted either from one or the other distribution, and we want to understand which was the right distribution. So the first way to model this is Gaussian models. I will present the spike-Dishart case, in which the null hypothesis is, as I said, pure noise. So we model it with a Gaussian distribution in which all the components are ID and with variance 1. Instead, the alternative distribution is a spike case. So there is still the white noise, but now we add a spike, which is made in this way. So there is a unit vector U, which is chosen like fixated at the beginning with some prior. Then there is a Gaussian variable G, and then there is this real parameter nu, which is the signal to noise ratio. So if this number nu is very small, then it's like if the spike is not there, and so it's pure noise. Instead, if the signal to noise ratio is very large, then the spike becomes much greater than the noise, and so we can see immediately the spike. But why did we choose that G is Gaussian? That is to make the whole distribution a Gaussian distribution. So the mean will be 0, and the covariance matrix is given by this formula. So it's an identity matrix, as in the null hypothesis. And so the only difference is a rank 1 spike on the covariance matrix, which is the norm of the spike is the signal to noise ratio, and the direction of is U times U transpose, which is a rank 1 matrix in the direction of U. So how to solve this problem? The basic idea is to see, okay, they are both Gaussian distribution. We can just look at the covariance matrix. So in the null hypothesis, it's the identity. In the alternative hypothesis, it's the identity plus some spike. So if we look at the eigenvalues of the matrix, the largest eigenvalue will tell us the difference of the two distributions. So if we get a sample of the distribution, let's say U mu from U going from 1 to n, then we can construct the sample covariance matrix, which is the approximation, empirical approximation of the covariance matrix done in this way. So we just average on the covariances of the samples. And so the idea of the spectral methods is to compute the eigenvalues of this sample covariance matrix and take the larger one and see if it's closer to 1 plus nu or instead just 1. So now we have to talk about which regime we are studying this problem. So in the classical regime, what I say will work, and by what do I mean by classical regime is just that we fix P, so the dimension of the system is fixed, and then we gather more and more samples, so n goes to infinity. In that case, Sn by law of a large number will converge to the actual covariance matrix of the distribution. So if the null hypothesis was the right distribution, then we will see that Sn will converge to the identity, so the largest eigenvalue will go nearer and nearer to the 1, and so we will be able to distinguish it, because instead if the right distribution was the alternative hypothesis, then the larger eigenvalue of the sample covariance matrix will go to 1 plus nu. But what instead is the high-dimensional regime, which is the one that is more used now in the applications, because in application the dimension of the system P is so large that it's not even more realistic to consider that we will have so many samples that the dimension will be negligible. So a better way to model this is instead to consider both the dimension and the number of samples to go to infinity together, and taking some conditions on the way they go to infinity. For example, the ratio, we fix the ratio. So this gamma is a constant in which, so both P and N will go to infinity, but with this ratio constant. And what happens is that it's rather surprising that what the classical regime, what was happening, all these convergences of matrices don't happen anymore. And then, if we consider just the null distribution, so the distribution is Gaussian OID, so it should be the simplest thing in the world. But what happens in the high-dimensional regime is that the limiting distribution of the eigenvalues is not what we will think that it concentrates around the eigenvalue 1, but it indeed the limiting distribution is the following, given by this picture. This is a result that has been proved in the 70s by Marchenko-Pastur. So, which is like a completely analytic density given also by this formula, which is quite different from maybe what we would have expected, but still it's an explicit formula. So thanks to this convergence, we know what's the behavior in the null hypothesis. So now we can see what happens in the alternative hypothesis. And so we can see that here we have two plots. On the left, we have a very small signal-to-noise ratio, so it's 0.5. And indeed, like the histograms are the eigenvalues of the matrix, and the solid line is the Marchenko-Pastur distribution. So we see that they match perfectly. So if there is very little signal-to-noise ratio, the distribution, the limiting distribution of the spike distribution is the same as the Marchenko-Pastur. Instead, if we take a bigger signal-to-noise ratio, then we can see that there is like all the eigenvalues follow the same law except one, which pops out of the distribution. So in this way, we can distinguish that this is indeed the alternative distribution and not the null hypothesis. Okay, so this is what happens, like taking two values of signal-to-noise ratio, but indeed it has been proved by Benarou, Bake, and Pechet in 2014, I think, that this is indeed the general picture. So for all signal-to-noise ratio below 1, below not 1, but this thing here. For all signal-to-noise ratio below the critical value of square root of gamma, the left picture happens. So there is no eigenvector that pops out from the distribution. And indeed, they prove that this is not some problem of this model, but indeed the two distributions are indistinguishable for signal-to-noise ratio below the critical value. And instead, above the critical value, there is distinguishability, and this algorithm can distinguish. So just computing the largest eigenvalue of the sample covariance matrix will give an eigenvalue that it's outside the support of the Marchenko-Pastur distribution, and this will allow to distinguish the two models.
But what is that?
Yes, that's a mistake because it's new.
It's new, okay.
I changed the notation, but in the plot it's the same. So this is signal-to-noise ratio 0.5, and this is 2. Thanks. There are also other consequences of this phase transition. Indeed, it's also possible to recover the spike, because up to this point, we just mentioned about distinguishing the models. So a priori, an algorithm could distinguish the models, but without giving any information on the signal inside. Instead, this method allows to recovery. So like what happens is that we computed the eigenvalues But if we also consider the eigenvector of the largest eigenvalue, it will be correlated with the spike. So, and the formula is the following. So if the signal to noise ratio is below the threshold, there will be no correlation. Instead, as soon as we get above the threshold and there is distinguishability, the largest eigenvector is correlated to the spike according to this formula, which will go to 1 as nu goes to infinity, so we will be able to retrieve the whole spike. This is a priori estimate, like in reality, we don't know the spike. In this way, we could use the largest eigenvector as a way to estimate the spike. And also another practical remark is that now that we have this theoretical model, we have also estimates, a priori estimates on the sample complexity, which is like what's the useful number of samples that we have to extract from the distribution. So if we just play around with the formula, then we get that if we take a number of samples n, it's on the order of p over the signal to noise ratio squared, then in that case, we will be able to distinguish the two models. That's useful because in practice, sometimes you have an algorithm on a model and you have the answer. So you have some number that the algorithm needs, but you don't really know if it's just detecting noise or if it's detecting something more. And now you have an estimate that, okay, if I have more than n samples, then it's really finding some structure in the model. So now there are some simulations. So to test this, to have some practical confirmation of the law, we can just create fixed p, create some instances with different values of n, compute the sample covariance matrix, extract the leading eigenvector, and compare its overlap with spike. And indeed, what happens for different dimensions is that, okay, the solid line, purple line, is the prediction of the BDP model, and the other lines with the error bars are different simulations, but we see that the behavior is exactly matches the prediction. Okay, so this was everything for the Gaussian model. Now we see beyond Gaussian models, because the starting problem is that if we compare it with real-world data, so this is a picture taken from the paper Golting, Rosso, Refinetti, in which we see each column is some all the images that should portray the label on the top. So we have airplanes, where automobiles, birds, cats. Okay. The first image is taken from a data set of real pictures that is not high quality, but we can really see this is an airplane, this is a car, this is a bird. While the lower two rows are Gaussian approximations of the same data set. So this this picture is like a Gaussian approximation of all airplanes. So taking just normals and just Gaussian normals are just averaging on all the airplanes, you get this thing. This is Gaussian, but with the right covariance. And the below two rows are instead neural networks approximations. So what we see is that Gaussian approximations are not very good, because this is just looks like pure noise. This is, okay, maybe works better, but still, I say, worse than maybe neural networks. So this is just the motivation to say, okay, real world data, it's not really Gaussian usually. And indeed, what you can see is that most of the information of real world dataset is not conveyed, like you can't see it just looking at the mean and the covariance of the dataset, but you have to look at more complex correlations of the dimensions. And the problem is that Gaussians just can model mean and covariance, because that's just the degrees of freedom. So we need to understand better like how the information is conveyed in the higher order cumulants, which is the higher order correlations of the dataset beside mean and covariance. So let's start recalling what cumulants are. So we can define the cumulant generating function, which is very similar to the moment generating function. It's just the logarithm. And as we do to define moments, we can expand it in Taylor series. we will have a series with either degree, polynomial degree, and we just name the tensor order n tensor. That's the coefficient of the order n term in this series, the cumulant. So cumulants, low order cumulants are very well known because order 1 cumulants are just mean values. Order 2 cumulants is just the covariance matrix of the data. And for Gaussians, it stops here because if you compute the cumulant generating function, it's this function, which is an order 2 polynomial. And indeed, it's all the other cumulants, so beside the order 1 and 2 are all zeros. So that's why I said that Gaussians cannot pick in the data cumulants that are above order 2. So let's get some intuition on what higher order cumulants tell. This is an example of order 3 and order 4 cumulants, which is, so order 3 cumulants is called the skewness and measures this asymmetry of the data. So for example, this is a stupid example, but the exponential variable, which is not symmetric, is positive skewness. And the only problem is that for all the symmetric distribution, the skewness is 0. So it's not so much used. It's more used the kurtosis, which is the cumulant of order 4. And for example, here we see some 3 distribution, which have, they match all the moments up to the 4th order. So, and they just have different kurtosis. So kurtosis also can be used to measure how fast a distribution goes to 0. So for example, we see Laplace distribution, which has a fat phase compared to the Gaussian. And so it has positive kurtosis, it's kurtosis 3. We have a Gaussian which has 0 kurtosis, and all the compactly supported distributions, so they go to 0 immediately, and so have a negative kurtosis. So for example, the uniform distribution has minus 0.2 kurtosis. So now we have to design a model to try to investigate these higher order cumulants. So the aim is to create something that is similar to spiked Wishards, but in which low order cumulants give no information. And all the information is provided by higher order cumulants. And also we still want to keep the interpretation of the model as noise versus signal plus noise. So the idea, the first idea that comes to mind is to just like seeing that spiked Wishart indeed was a model in which there were 2 distributions, and the difference between the 2 distributions was in the covariance. One had identity covariance, the other had identity plus one rank 1 spike. So an idea could be, okay, just let's spike an higher order cumulant. And a way to do it is the following. So we keep as null hypothesis random Gaussian noise, ID Gaussian noise. And then we, as alternative hypothesis, we consider the following distribution. So as before, we have still the noise, then we still have the spike, but now we also have a pre-processing matrix. And so as before, U is a unit vector of which is extracted with some prior, but this time H, so the distribution of the spike is not Gaussian anymore, but it's some non-Gaussian distribution that has a structure in the higher order cumulants. We keep the signal to noise ratio, and then we use this matrix S to scale the data in such a way that its covariance matrix is the identity. So that we, as we said, we don't want the covariance to give information about the model. Otherwise, we could solve the problem without looking at the higher order cumulants, and it wouldn't make sense. So now we can, okay, we compare with the spiked Wishart model. So we can see that it's still same null hypothesis, still a spike structure, but then the spikes are different. So the spike is non-Gaussian. And now we can compute the cumulants. So as we expected, the first cumulants, so the distribution is centered, so the first cumulant is 0. The whitening allows the covariance to be 1. And now if we take the non-Gaussianity H to be a symmetric distribution, then also all the odd moments are 0. And now, since we have a rank, the non-Gaussianity follows the direction of U, then the kurtosis can be proved to be a rank 1 tensor in the direction of U. And for the moment, we don't know anything for all the other even moments, because the odd ones, if we take H even, are 0, but we don't know anything about the even ones. So we still have to choose explicitly H. So one question could be, can we choose it so that we isolate just the kurtosis and all the other cumulants are 0? Indeed, it cannot be done, because there is a result that proves that besides constants and Gaussians, all the other distribution have non-polynomial cumulant generating functions. So since we don't want neither a constant or a Gaussian to be H, then it will be forcibly have infinitely non-zero cumulants. And so this is something that we need to cope with. We cannot solve it. Now let's talk about what we want to do with this model. So we will sample. And so we will have a data matrix Y underline, which is P times N. So P are the dimension of the data, then which are the rows of the matrix, and the columns are given by I the samples of the distribution. And now we investigated the I-dimensional regime. So we let both P and N go to infinity. And we want to ask, depending on the non-Gaussianity H on the signal to noise ratio, what's the right sample complexity? So what's the interesting way to make N and P go to infinity? We saw in the Spike Lee chart that they were linear, so we were taking the ratio fixed, but a priori it's not given that this is the right scale and what we want to find out. A comment about the technique that could be used. So before we saw that we were using spectral methods and random matrix theory, but that was just because the structure was in the covariance matrix and we could just take sample covariance and do a spectral analysis on that. Now the information is in the higher order tensors, so we could need to have some random tensor theory. It's even more complex than that because there are infinite non-zero cumulants, so we cannot restrict just to one cumulant. So maybe it's better to have a more indirect approach. And what we propose is based on the low degree likelihood ratio and the second moment method. So I have to introduce some notation. So we have sequences of measures at this point because we have the null hypothesis I denoted with the letter Q, the alternative hypothesis with the letter P. But since we want to take N and P to go into infinity, we will have a sequences of measure for each value of N and P. And so how to define distinguishability of measures, of sequences of measures. A possible definition is that there exists a sequence of event AK, such that the event has vanishing probability according to the null hypothesis, and its probability converges to 1 according to the alternative hypothesis. Such a way, if that this event happens, then we know the right hypothesis is the alternative one. If the complementary happens, we know that the right hypothesis is Q, the null hypothesis. So let's now define the likelihood ratio, which is the Radon-Nikodym derivative of the measure P with respect to the measure Q. And in this case, since it's everything absolutely continuous, we can just take the ratio of the densities. And I just mentioned what this property that will be used is that thanks to the change of variable, if we take the expectation of the likelihood ratio with respect to the null hypothesis, we can just, in this formula, substitute the definition, and we just have that it's nothing else than taking the expectation of the variable according to the alternative hypothesis. So now we can define a structure of Hilbert space by defining this product F and G, which is essentially the L2 product weighted with the density of the null hypothesis, which I recall that it's ID Gaussian, and that's important. So I am ready to state the second moment method, which is a necessary condition for distinguishability. And so it basically says that for P and Q to be distinguishable, you need that the norm of the likelihood ratio to explode. That's also pretty realistic, because if you want to have some sequence of events that goes as zero probability, it goes to zero according to Q and goes to one according to P, then the ratio of the density in that region has to explode. But the problem with the likelihood ratio is that it's very hard to compute. So it's not really realistic to imagine to be able to compute it and compute the norm. So we will use instead the low degree likelihood ratio. So we define it, we consider the fixed D degree. We define the low degree likelihood ratio of degree D as the projection of the space of polynomials up to degree D of the likelihood ratio. And we project along the metric defined by the Hilbert space, this metric that I defined before. So this object is linked with if the likelihood ratio is linked with the equation of distinguishability. Instead, this one is linked also with the question of distinguishability in polynomial time. So if the norm of the low degree likelihood ratio goes to infinity, there is also evidence that there will be likely exist polynomial algorithms able to solve the problem. And also, like from a more like this property is more interesting to us. If we fix the low degree polynomial, the low degree likelihood ratio of degree D, sees the two distribution with that degree. So it won't see information that it's in the cumulants that are of higher order. And also, that's practical remark, it's easy to compute if the null hypothesis is a Gaussian, because we can use Hermite polynomials. So I recall what Hermite polynomials are. It's just a family of polynomials that using the product that I defined before, they are orthogonal, and they form an orthogonal basis of the Hilbert space. So if we want to compute the projections, we just need to do the following. So take the likelihood ratio and compute its component against each of the Hermite polynomials. And indeed, if you use the formula that I defined before, we see that it's not even necessary to know the likelihood ratio. So we can, in this formula, it simplifies, it's just necessary to take the expectation of the Hermite polynomials with respect to the null hypothesis, to the alternative hypothesis. So to recap, what is the use we want to do of the low degree likelihood ratio is so here we have the formula for the norm, where we want to compute the norm. And so if it's always bounded, then we can deduce that it's P and Q are indistinguishable. Instead, if it will go to infinity, then we deduce that it likely the two hypotheses are not distinguishable. I say likely because it's not, it's just a necessary condition. It's not a sufficient conditions. And indeed, there are counterexamples. So let's see the application to the model that I described before. So I recall what we will need about the model. So we want that all the cumulants up to order 4 are trivial. Order 4 cumulant is just in the direction of U. And as a prior on U, we take ID Gaussian. So Gaussian with some variance sigma. And to have the right scaling, we take the variance to be proportional to 1 over square root of P. Otherwise, taking P going to infinity, we would have also the spike, the norm of the spike going to infinity, and it will be trivial to distinguish the two models. In this way, the norm of U stays around 1. So with this hypothesis, it's possible to bound from below the low degree likelihood ratio norm with the following quantity. And so in particular, if n is much larger than the degree D, we can have this bound, which hints to the fact that, so in this bound, we can see that if n is greater than p squared, the limit at infinity will go to, will diverge. And so this is the condition for distinguishability, we said. So let's compare what we know about spiked-Wishart and what we know about this model. So in spiked-Wishart, I put equal here because we really know this is the right scaling for sample complexity. Instead, for the moment here, we just have an inequality. So if we know that if n goes to infinity faster than this, then likely there is distinguishability, but we don't know anything else at the moment. But the nice thing is that the scaling is like what we would expect, because now in the spike-to-Bishop case, the spike was in the covariance matrix, which should be easier to detect than a spike on the kurtosis, because to access the kurtosis, you need usually many more samples to be able to approximate it. And indeed, we see here that we will need many more samples because it's quadratic in P and not linear. Now let's see what happens in simulations. So to simulate this problem, we can fix the dimension P and create various instances for the different values of n. Compute the empirical approximation of the kurtosis, which is so a tensor like the sample covariance matrix, but for the kurtosis. Extract the leading CP factor, which is like the analog of extracting the largest eigenvector, but like not really the analog, but in this case it will do. And then just compute its overlap with the spike. And what we see doing some different runs is that there appears to be some phase transitions, and they always seem to like deviate at the same point. And this scale of the plot is indeed number of samples over the dimension squared. So this is evidence that the scaling found by the previous inequality is the same for this simulation. And so we can finally compare with the spike-to-Bishop case. And just a remark, as you see, the dimensions here are much larger. Here are just ridiculous dimensions. But the problem is that this simulation takes much more than this one, because the big problem is that I needed to estimate the whole kurtosis tensor, which is something that becomes very hard for my computer above dimension 20. Instead, like dimension 1000 for the covariance is not a problem. So just a perspective on the future work. So we need to improve on the estimate for the low degree likelihood ratio and maybe compute an exact formula, but it could be very hard. Then find the repeat simulation with different values of H, because I didn't mention, but we just use a specific value for the non-Gaussian distribution. So also interesting to find the best one or most interesting one. And this is very important. So to make simulation, we find a way to solve the problem without needing to compute to approximate the whole kurtosis tensor, because we just like basically we need to estimate the whole tensor and then extract just one information about the largest CP factor. And then there is also the whole problem about the retrieval problem, because for up to now we just investigated the hypothesis testing setting, but we don't have no mathematical way to address the retrieval problem, because this low degree likelihood ratio cannot be applied in that case, because it's just for hypothesis testing. Okay, so I finished. Thanks.
Thank you for the nice talk. Now it is question time. So online you can simply unmute yourself and ask if you want. From the room you can.
What you call the CP component of your
CP factor, yes. It's a good question, because I didn't really have time to enter into this, but there is the problem of, like, for matrices, we can diagonalize them, we can find eigenvector, eigenvalues. For tensors, it's not so clear, like, what we can do. Like, we can take a tensor and try to, like, write it as a sum of low-rank tensors, but it really has not the same properties of decomposing a matrix. So, for example, tensor PCA is like, for example, you cannot do find just the largest eigenvalue and then do it iteratively, but you really need to like develop the whole tensor. So it's very time consuming, and it's not really. Another problem is that you cannot really well foresee the properties of the CP factors as you do with eigenvalues and eigenvectors. Also, from a theoretical point of view, it's harder.
And as a theoretical point of view, also results like
Yeah. Yeah, I don't think there are. I mean, there is. It's developing. But,
and the result, the first result you mentioned about.
Yeah, the Marchenko-Pastur. Yes.
Where?
That
you have a phase transition for the largest
BBP phase transition. Yes.
And for the CP factor, you don't have this kind of.
Exactly. Yeah. For the moment, no. I mean, it's a field that it's developing, but still we don't have those results.
Any remark on the applicability of for neural networks?
For neural networks, yeah, the idea is to get sample complexity bounds that really would help for simulation with neural networks. Because if you are using neural networks on a data set, there is sometimes the problem that you don't know when to stop. Like, did it find all the structure in the data set, or you should make it run more? If you have an a priori estimate on the number of samples that you will need, or the number of steps that the neural network will need to do, that would be useful also for applications.
But I generally measure whether my distribution has converged or not using real divergence or something like that. And then if I want to use your work, so I will. I'm just thinking. Correct me whether I'm actually going to have right or wrong. So then I would get an estimate with the dimensionality, with how much accuracy I should be obtaining, probably as a function of dimensionality or something. Like
that. Something like that. In a very specific case, like in this case in which you have noise versus, like in all the cases in which you don't know if your data is just noise or there is some very small structure inside. This estimate could be applied, because like sometimes you don't have other ways to find if it's converging. Like,
no, you can use real divergence to have something like that. So whatever is your target probability distribution you're looking at, but that's okay. Have you tested with any cases?
No. For the moment, we still that's something we still have to do. Like, it's still in the beginning, so we didn't test. Like the whole test we did is this counts, but it's like not really, like it just was to make some picture here and like add some it's not realistic way to test it. The algorithms.
Fair enough. So, and in the slide where you had like those pattern of pictures, you mentioned pattern of pictures. Long time I've seen this. So are we talking something on the lines of GANs in here?
Yeah. The third for the row is GANs.
And you feel like it's something for some your work would be much more suitable to GANs, or you think like I can do more stuff with like CNNs and other application areas? Because if you're talking about noise GANs, it's your ideal candidate for sure. But what do you?
No, like I think like this is a result that it's independent of the architecture, so it could be useful for any architecture. Like the point of this slide was just to emphasize that Gaussian models are not like very useful to extract information from the data, and there are algorithms like neural networks that manage that.
Okay, I think I understand your point. Thank you.
If there are no other questions, we can thank Lorenzo again. Yes.